Now let's look at the proof of the lemma. Given two pairs of camera projection matrix, which we denote as PP prime and P tilde and P tilde prime, they have the same fundamental matrix, which is essentially given by the first cross product here, A cross with capital A, and this is also equals to A tilde cross product with capital A tilde. And we saw this relation earlier on. We also know that if we take the cross product of a vector by itself, that means that if I take the cross product of A cross with itself, this is always going to be equals to 0. Hence, taking advantage of this particular relation over here, when we can do this A transpose with A cross product of A, this equation here simply is equivalent to A cross product of A by itself transpose, and this is always equals to 0, and multiply by A, and this will give us 0. This simply can be rewritten into A transpose F equals to 0, which means that A is in the left null space of F over here. And similarly, we can write the relation in the with the second pair of camera matrices, which gives us A tilde transpose F equals to 0. And this simply also means that A tilde is in the left null space of the fundamental matrix. And since both A and A tilde are in the left null space of the fundamental matrix, this simply implies that A tilde is equals to A multiplied by a scalar value, which we call K over here. Note that this is a non-zero scalar value of K. And next, we can see that since the fundamental matrix obtained from the two pairs of camera matrices are equal, we can write this relation over here. And according to what we have proven earlier on, that A tilde is simply equals a scalar non-zero value K multiplied by A. We can substitute this relation here into this equation here. And as a result, we will get A cross 3 by 3 matrix of A. And then here it's simply a scalar value multiplied by A cross product and multiplied by the 3 by 3 matrix of A tilde over here. And since K here is a scalar value, we can actually factorize it out. So this means that by moving the left hand side to the right hand side, this simply means that we get this particular relation over here, which is A tilde minus A equals to 0. And this is simply this guy over here. And so once we have this particular relation, this tells us the relation that the cross product of A with this particular matrix over here, the 3 by 3 matrix over here, it has to be equals to 0. And according to the definition that we have seen earlier on, if we take the cross product of any vector by itself, it's always going to be equals to 0. So we can simply rewrite this part over here, K multiplied by A tilde minus A, as a dot product of two vectors, A and an arbitrary vector of V transpose, where A simply cross with itself over here, which is this guy over here, would give us 0. And hence, we can conclude that K of A tilde minus A can be rewritten as A multiplied by the transpose of an arbitrary vector that we denote as V over here. And by rewriting this equation into making A tilde the subject, we will get this equation over here, which is exactly what we have defined earlier on. Hence, this completes the proof for the lemma. So putting the lemma back into the earlier proof that we are trying to show, which is two sets of camera matrices, P, P prime, as well as P tilde and P tilde prime. If they both give rise to the same fundamental matrix, this simply means that P is related to P tilde by a 4 by 4 non-singular projective matrix, as well as P prime is also related to P tilde prime by a 4 by 4 non-singular projective matrix H over here. So putting back the results that we have seen earlier on in this particular lemma, if we were to write the second camera matrix from the respective pair as A and A tilde over here. We get this particular relation that A tilde equals to KA, and the 3 by 3 matrix of A tilde equals to this relation over here. Putting these two relations back into the pair of camera projection matrices, we will get this particular results over here, where P and P tilde still stay at the canonical representation, which is I and 0, but P prime and P tilde prime now becomes this particular form of A, and then the P tilde prime would be related to the first camera matrix in this particular form, which is shown by the lemma earlier on. And it is not difficult to see that now P and P tilde prime, these two camera matrices, which is the second view of the respective camera projection matrix pairs, it's actually related by a 4 by 4 matrix given in this particular form, where K here is what we have defined earlier on to be a non-zero scalar value, and V would be an arbitrary 3 by 1 vector that we have defined earlier on. Hence, they are altogether 4 degrees of freedom inside the particular H matrix over here. And it's not difficult to see that when we take P multiplied by H, we will get this particular relation, which equals to K inverse multiplied by P tilde. And this simply supports our claim earlier on. If the two sets of camera projection matrices give rise to the same fundamental matrix, then P tilde, which is the first camera of the second set of camera projection matrices, is going to be related to the first camera matrix of the first pair by a 4 by 4 non-singular projective matrix H over here. And indeed, this is true up to a certain scale, since K is an arbitrary non-zero scalar value that we have seen earlier on. So this equation here is proven to be true. And furthermore, we can also show the same relation between the second camera. So we have P prime and P tilde prime. Previously, we shown this relation between the first cameras, and now we can see that the same relation by the projective matrix H that we have defined earlier on holds true for the second cameras in these two sets of camera matrices. And it's not difficult to plug H into the equation over here and simplify this expression. We will get A tilde 3 by 3 matrix with the A tilde 3 by 1 vector, which is simply equals to P tilde prime. I'll leave this to you to verify that this particular relationship is true. And so we can conclude that P and P prime, the first set of camera matrices, is indeed related to the second set of camera matrices, P tilde and P tilde prime, if they both result in the same fundamental matrix. So this completes our proof. Now, having proven that a fundamental matrix can be decomposed into a non-unique set of camera matrices P and P prime, which is given by this guy over here, F is decomposed into P and P prime, or simply a set of a family of solutions which is related by a 4 by 4 projective transformation matrix H over here. So these are all equivalent decomposition of H. Now we're going to specify to a certain method to decompose the fundamental matrix. But before we do this, we need to specify this particular relation, that a non-zero fundamental matrix F over here. It corresponds to a pair of camera matrices P and P prime, if and only if this relation here is skew symmetrical. We can see that this is true from the following proof over here. Starting from the equation, the correspondence equation that we have seen earlier on, where x prime transpose F multiplied by x equals to 0. We can see that this equation here can be rewritten into P prime multiplied by the 3D coordinate x transpose F, and P multiplied by x equals to 0. And this implies that this can be rewritten into x transpose P prime transpose F and P X equals to 0, which means that in this particular case here, we can check that this guy over here always has to be a skew symmetric matrix in order for this correspondence equation to remain true. Hence, we conclude that in order for F to correspond to a pair of camera matrices P and P prime, this particular relation here that we've seen earlier on here must always be skew symmetric. And as a result, we can choose the decomposition of F into P and P prime in the following form, where the first camera projection matrix P can be chosen at a canonical setting, which is equals to identity, a 3x4 identity matrix, and the second camera projection matrix can be chosen as the following form over here, where the first 3x3 matrix over here is simply equals to the cross product of the epipole multiplied by the fundamental matrix over here. And the last column in P prime is simply given by the epipole of the first view. You can actually verify that pair of camera matrices give rise to a skew symmetry, which is shown by this guy over here, P prime transpose multiplied by F multiplied by P. It must be a skew symmetric matrix. We can easily show this by substituting this particular equation over here. So we have starting from P prime transpose F multiplied by P over here, where P prime here is simply this guy over here, so this is the epipole of the second view. So what it means is that we'll have to substitute this into this equation over here, where this is the form over here that we get here. We denote S over here simply as the skew symmetric metric of the epipole in the first view, and we'll get this form over here, and where P over here is simply the identity 3x4 matrix that we have seen earlier on. After evaluating this matrix multiplication relationship, this is what we get over here, where we know that the dot product of the epipole multiplied by the fundamental matrix is equals to 0, since we have seen earlier on that the epipole is actually the left null space of the fundamental matrix. So this guy here is equals to 0, and hence we can show that since S over here is defined as the skew symmetric metric, which is the skew symmetric metric of the epipole, the multiplication of any arbitrary 3x3 non-zero 3x3 matrix, which is the fundamental matrix, with this skew symmetric matrix is always going to be a skew symmetric matrix. Hence, this proves that the choice of P and P form over here is going to give rise to a skew symmetric matrix when we plug these two, the P and P prime, into this equation over here. Hence, this shows that P and P prime in this form is a valid decomposition of the fundamental matrix. Now, so far we have looked at the fundamental matrix under an uncalibrated setting. This simply means that we do not know the camera intrinsic value K and K prime in the two views. But in the case where we know these two camera matrices K and K prime, we can simply rewrite the point correspondences X, small x and X prime in two views. So X and X prime is the point correspondences X, and then X prime point correspondences in the two views. We can simply rewrite this since we know K and K prime, the camera intrinsic value. We can simply rewrite this into K inverse X and K prime inverse X prime, and we call this the normalized camera coordinates. So, and we denote this correspondences after we normalize it with the camera intrinsics as X hat and X hat prime over here. So now let's substitute this particular normalized camera coordinates into the correspondence equation of the fundamental matrix that we have seen earlier on. X prime, which is X prime transpose F X equals to 0. So after we normalize this, since we know that the camera intrinsic value, we can replace X prime over here using K prime inverse multiplied by x prime and transpose of this. And then we have to replace F with some other matrix, which we now call it E over here. And in order for the relation to still be valid, because we introduced the camera intrinsics over here, so we have to replace the fundamental matrix with some other matrices, with another matrix which we call E over here. So X, similarly for X, we are going to replace X with the normalized camera coordinates, which is K inverse multiplied by X over here, and this is equals to 0. So after we apply this transpose, we will get X prime transpose K prime inverse transpose E multiplied by K inverse X, and this is equals to 0. And we can see that this takes the same form as the original correspondence constraint equation that we have seen earlier on, which is x prime transpose f x equals to 0, and where this x prime and x remains the same, and we can simply call this particular matrix over here our fundamental matrix, and we'll give the E matrix over here a name. We'll call this the essential matrix, with the relation of F is simply equals to K prime inverse transpose E K inverse. And we can simply also rewrite this equation by grouping the normalized camera coordinates together. So we can call this guy and this guy here as our normalized camera coordinates. And now we'll get the correspondence constraint equation in terms of the essential matrix as well as the normalized camera coordinates, which is x hat prime transpose E multiplied by x hat equals to 0. We'll see that E can be decomposed into the cross product of the translation vector and the rotation matrix. Here's the proof that the essential matrix can be decomposed into the cross product of the translation vector multiplied by the rotation matrix. Previously, we have seen in the algebraic derivation that the fundamental matrix can be expressed as the cross product of the epipole in the second image multiplied by P prime, which is the camera projection matrix in the second image, and P inverse, which is the pseudo inverse of the camera projection matrix from the first image. And since we express the camera projection matrices as a canonical representation, so the first camera projection matrix would be equals to K multiplied by a 3x4 identity matrix, and P prime over here would be equal to K prime multiplied by the transformation R and T. I'll leave this to you to verify that the pseudo inverse of this particular 3x4 matrix over here, it's equal to a 3x3 K inverse over here, and the last row to be all zeros. Since the first camera is defined in the canonical frame, this means that the first camera center is going to be the origin of the world frame, because it's the camera coordinate frame aligned with the world frame in this particular case. So now let's substitute these two equations. Pseudo inverse of the first camera projection matrix and the camera center of the first view into the fundamental matrix equation over here, and expressing this, working out the expression over here, we can see that this particular expression over here evaluates to this equation. I'll leave this to you to prove that K prime in a cross product or skew symmetric matrix and K over here can be factorized to become K prime inverse transpose multiplied by the skew symmetric matrix of T multiplied by R and K inverse, which remains from what we saw earlier on here. And hence, since we know that the fundamental matrix is equals to K prime inverse T cross with R and K inverse over here. No, this is exactly the relation that we have seen earlier on here, where now we have proven that E, the essential matrix here, is indeed the cross product of the translation vector and the rotation matrix. So now let's look at some properties of the essential matrix. Overall, the essential matrix has 5 degrees of freedom, where 3 degrees of freedom comes from the rotation matrix and 3 additional degrees of freedom comes from the translation vector. So this adds up to be 6 degrees of freedom. But because the translation vector here, it's only defined up to scale. There's overall scale ambiguity. Hence, we have to take away 1 degree of freedom from this 6 degrees of freedom. So 6 minus 1 will give us 5 degrees of freedom in the essential matrix for a calibrated set of cameras. And essential matrix, since it's a rank 2, which means that the third singular value of the essential matrix is going to be equals to 0. And in comparison to the fundamental matrix, where it's also a rank 2 matrix with the third singular value equals to 0. In the essential matrix, we have an additional constraint where the first 2 singular values must be equal. This means that if I were to take the SVD of E, I will get U sigma V transpose, and I will see that sigma is actually equals to the first singular value, second singular value, which are equal, and the third singular value should be equals to 0. Now we'll look at how to decompose the essential matrix into a given essential matrix into the translation vector and the rotation matrix. So we'll start from this particular equation that we have seen earlier on, that we have proved that E equals to the cross product of the translation vector and the rotation matrix. So given E over here, given the essential matrix, which is essentially a 3 by 3 matrix over here, we take the SVD of E, and this will simply give us the left octagonal matrix and multiply by the singular value and the V transpose, where V here is equals to the right octagonal matrix. We can simply rearrange this taking U and V, and such that we multiply U by a matrix which we define as Z over here. So if you take U, which is an octagonal matrix, multiplied by a matrix 3 by 3 matrix that we define as Z over here, and U transpose, the end result of this would be a skew symmetric matrix. So now what it remains is that we have to further find out what's the representation for Z over here. But suppose now we have this representation, which is Z. We'll try to find Z such that the expression over here gives rise to a skew symmetric matrix that corresponds to the skew symmetric matrix of the translation vector over here. And we can also do the same trick where we take the left octagonal matrix multiplied by some matrix over here, which we call X. This is also a 3 by 3 matrix over here, multiplied by U transpose. Since these two are octagonal matrix, we just have to figure out what's X over here, such that it will also give rise to an octanormal matrix of R over here. So this end result over here would be equal to the rotation matrix here. Now, what remains here is for us to figure out what's a suitable matrix to represent Z as well as to represent X. And we can check that since there's a U transpose here multiplied by U, and since U here is the left octagonal matrix, U transpose multiplied by U would simply be equals to identity over here. So we can evaluate this particular expression over here, the product of these two expressions over here, into this form over here. And we can see that this is simply equivalent to the SVD of taking the singular value decomposition of the essential matrix over here, where U and V transpose is simply equals to the left and right octagonal matrices of the SVD of E, and we'll have some clue over here that Z multiplied by X should be equal to the singular value, the diagonal matrix. So sigma over here should be, as we have seen earlier on, should be equals to sigma, sigma, and 0, where the off diagonal are 0. And this should be the result of Z multiplied by X over here. And since E here is known up to scale, because we saw in the property here that the translation vector over here, it's there's an overall scale ambiguity. That's why minus 1 degree of freedom here. we can ignore the sign of z and x. What this means is a suitable choice for z and x when multiplied together, it should give us this end result over here. Would be z equals to this matrix over here, and w equals to this particular matrix over here. And when we multiply these two together, z multiplied by w, we'll get a diagonal of 1, 1, 0, which is equivalent to this. Since it's known up to scale, this simply means that we can put unit scale in this particular diagonal singular value matrix over here. And we also do not know the sign. What this means is that the diagonal matrix could also be -1, -1, and 0. And this is which is simply given by z multiplied by w transpose, where x equals to w transpose over here. So after we have recovered the left and right orthogonal matrices from the SVD of the essential matrix of E here, and we also have defined the matrices of W and Z, which we have seen in the earlier slide, we can now go on to recover the translation vector, where we previously defined that the skew symmetric matrix of the translation vector T is equals to U multiplied by Z multiplied by U transpose here. And since U is a octagonal matrix and T is a skew symmetric metric, we can get this relation where the translation vector would be simply obtained as the plus minus third column of the left octagonal matrix U from the SVD of the essential matrix E. And then once we have recovered the translation vector, we can also concurrently recover the rotation matrix as equals to be U multiplied by W V transpose, or U multiplied by W transpose V transpose. This is because we have defined W here to be equals to this matrix over here, where we can concurrently obtain the diagonal of 1, 1, 0 or -1, -1, 0 to suit this singular value matrix over here. And hence W can be either W or W transpose. Hence we'll get two different solutions for the rotation matrix by considering W and W transpose. And finally, we also have to make sure that the rotation that we obtain from this method follows the right hand coordinate as shown in this figure over here, where when we sweep our fingers from the direction of X towards Y, our thumb would have to be pointing towards the Z direction, and this is defined as the right hand coordinate frame using our right hand here. Similarly, we can define the same thing using the left hand, but we have to ensure that the rotation that we obtain over here follows the right hand coordinate. And this can be simply done by adding the if else condition over here. So if the determinant of R is lesser than 0, then we simply set R, which we have obtained from either of these two equations over here, to be minus of R. So from the previous slide, we saw that the translation vector can be equals to plus minus U of 3, and the rotation matrix can be equals to U multiplied by W multiplied by V transpose, or U multiplied by W transpose multiplied by V transpose. Hence, altogether, we will be able to get 4 possible solutions for the camera matrix of P prime, which is given by these 4 solutions over here. That is a combination of all the possible solutions of the translation vector and the rotation matrix that we have found earlier. And what this means geometrically is that given a point, this particular point could be first in front of both of the cameras. Second, it could be behind both of the cameras. And the third case is that it could be in front of one of the camera and behind one of the camera. And the last case here would be that the point would be in front of the other camera and behind one of the camera. And only one of the 4 solutions is physically correct. And that is the solution where the 3D point appears in front of both the cameras. And we can easily disambiguate the correct solutions from the 4 solutions by getting the solution with the most number of points that appear in front both of the cameras. Earlier on, we looked at the correspondence constraints of the fundamental matrix, which is given by X prime transpose F x equals to 0. And we said earlier on that the fundamental matrix here, this particular equation over here, simply shows that the fundamental matrix can be determined from the image correspondence itself without any other knowledge. So in this particular slides over here, and the subsequent slides, we will look at how to compute this using 8-point correspondences. So starting from the constraint equation that we have seen earlier on, x prime transpose f x equals to 0, we can see that this particular equation over here can be rearranged into this form. This simply means that we expand out this x prime, y prime, and then multiply by x, y, and 1. And so after evaluating this guy over here, we'll get this particular equation over here. And this simply means that we get one constraint on the corresponding pair over the fundamental matrix. And because this is one equation, that is one polynomial equation that is equals to 0, so we can rearrange this. And the cool thing here is that all the entries of the fundamental matrix is linear with respect to this particular polynomial equation. So what this simply means here is that we can rearrange this into a dot product of this vector over here that consists of only the entries from the point correspondence x and x prime, and with a 9 by 1 vector which we reshape from the 3 by 3 fundamental matrix over here. So this simply becomes a linear construct of the fundamental matrix. Since we know that F here is a 9 by 1 vector, by making use of at least 8 constraints, this means that we have 8 point correspondences. And each point correspondence is going to give us a row multiplied by F over here. So we simply stack these correspondences together, form at least an 8 by 9 equation over here in order for this null space equation to be valid. At the end, we will be able to solve for the unknown null space vector over here, which is F over here. In the case where we have more than 8 constraints, we can simply just stack them together to form an overdetermined homogeneous linear equation and solve using the same method. So the more point correspondence that we have, the better will be the estimate of the fundamental matrix. This is because all the observations here are going to be corrupted with noise, and this is essentially a least square equation that we are going to solve. So essentially, we're going to do the argmin of this over f, and more equation, more constraints simply means the result of this will be much more accurate, as we have seen earlier on when we talk about the homography estimation. So the solution over here, we get a f equals to 0, where a here is simply a m by 9 equation, and f over here is simply a 9 by 1 vector. We've seen earlier in the lecture on homography estimation that the solution of f here, of this homogeneous linear equation, simply lies in the null space of A. And what this simply means is that after we take the SVD of A, we will get U sigma V transpose. The solution of F here is going to be the last column in V. And similar to the homography estimation, a data normalization is needed. So the last thing that we need to do in order to get an accurate fundamental matrix is to ensure that the fundamental matrix has a rank of 2. This, which is what we have seen in the properties of the fundamental matrix. But the problem here is that in general, after taking the SVD solution of AF equals to 0, where we get the solution of F, and since this is a 9 by 1 matrix, and we reshape it back into a 3 by 3 matrix of the fundamental matrix, well, we have the problem that this particular matrix that is found from the homogeneous linear equation is in general not of rank 2 due to the noise in the A matrix over here, because A matrix is made out of all the point correspondences which is subjected to noise. So this fundamental matrix that's estimated from this linear equation over here algebraically is in general not going to fulfill the rank constraint over here. What happens here is that if the rank of the fundamental matrix is not equals to 2, we will see that since we are making use of the fundamental matrix, we have two views. We are making use of the fundamental matrix to transfer a point on the first image into an epipolar line in the second image. And we said earlier on that this is given by L prime equals to F multiplied by X. And we said earlier on that if there are multiple points on the first image and if we transfer all these multiple points into the epipolar lines of the second image, we said earlier on that all these epipolar lines, they should intersect at the epipole, which is denoted by E prime over here in the second image. And E prime here should lie on the null space, left or right null space of the fundamental matrix. Now, in order for this epipole to exist, we can see that since epipole lies on the left or right null space of the fundamental matrix, this means that F here must be less than full rank. If F here happens to be full rank, then E here would be a trivial solution. And what this simply means here is that if the rank of F is not equals to 2, this simply implies that E doesn't exist, which is geometrically shown here. We simply use F, where the fundamental matrix, the rank of the fundamental matrix is not 2, and we simply use this to map every single point from the first image to the epipolar lines in the second image, which is shown by the black lines over here. We simply see that the epipole doesn't exist because all these epipolar lines won't intersect at a single point. So what we are required to do is that after estimating the fundamental matrix from the linear equation over here, we need to enforce the rank constraint, which simply means that we need to make sure that we need to do the last step of making sure that the rank of F equals to 2, and we'll see how this can be done. So the most convenient way to find the correct fundamental matrix with a rank of equals to 2 is simply by replacing the fundamental matrix that is found from the equation AF equals to 0 by another matrix, 3 by 3 matrix over here, which we denote by F prime. And this F prime must fulfill the rank constraint over here. So this can be formalized as a minimization equation over here. Simply we want to minimize the Frobenius norm between the 3 by 3 matrix that we have found from the linear equation over here with the final fundamental matrix subjected to the rank deficiency constraint. That means that we want to find a F prime that is as close to F as possible, such that the rank of F prime is equals to 2 over here. And fortunately, the optimization here can be easily done by simply taking the SVD of the F matrix that we have found from the homogeneous linear equation earlier on. So after taking the SVD of this guy, so SVD of F, we will get the UDV transpose, where D here is simply since the fundamental matrix, since the F matrix that's found from the homogeneous linear equation is not rank 2, so this is in general going to be full rank because of the noise from the A matrix over here. This rank is in general going to be full rank. What this means is that after taking the SVD, we would have 3 singular values here, which means that which we denote as RST, where R is the biggest singular value and T is the least singular value. So since there's 3 singular value, and this actually supports our claim that the rank of F is equals to 3. So in order for us to find F prime over here that minimizes this optimization, the cost function over here, we can simply replace the least singular value T over here with 0. And then after replace the least singular value with 0, we put this back into the original SVD equation and pre-multiply it by U and post-multiply it by U transpose to get the final uh, fundamental matrix F prime over here. And we can assure that this minimizes the Frobenius norm, as well as, since the third singular value is 0, this the rank of this particular matrix over here is going to be equals to 2. Now, in summary, the 8-point algorithm to find the fundamental matrix is given by this pseudocode over here. So the objective is that, given at least 8 correspondences, xi and xi prime, we want to find the fundamental matrix such that the constraint equation, the correspondence constraint equation that we defined earlier on, has to be true. So the first step of this would be to do a normalization, and this normalization is a compulsory step which is done in the same way as the homography computation. So we will first find a transformation matrix and a scale that consists of the scale and the centroid of all the points. So this simply means we are going to shift all the points to have a centroid of 0, as well as the sum of all the scale should be equals to square root of 2, which is given by this equation over here. Then once after we have transformed this every point by this transformation to do normalization, we can simply compute the fundamental matrix, which is F prime hat over here, by the normalized image correspondences over here. Then using the linear 8-point algorithm, so this is simply solving AF equals to 0. And then finally, we will enforce the singularity constraint by finding F prime. So this is just the Frobenius norm F prime arc mean over F prime subjected to the determinant of F prime must be equals to 0 to make the fundamental matrix a valid fundamental matrix with rank 2. After we have found the fundamental matrix over here, we need to remember to denormalize to recover the correct fundamental matrix. Same set of algorithm can also be done to find the essential matrix over here. And so it's also a 8-point algorithm, a linear 8-point algorithm for the essential matrix, which is given by this equation over here, x transpose t hat, where this is the normalized camera image coordinates of the second view, and multiplied by e and x hat equals to 0 over here, where x hat prime and x hat are correspondences over here. So we will simply first compute x hat and x hat prime over here from the original image correspondences x and x prime by simply taking the inverse of the camera intrinsic matrix and multiply it with this to get x hat prime. And we'll do it the same thing for the first view, k inverse multiplied by x equals to x hat over here. So once we get this, we simply make use of this correspondence in the camera normalized coordinate to compute the equation of a e, which we denote as this vector over here. So this note that this vector, not the epipole, we are just simply overloading the notation over here, equals to 0. This is a 9 by 1 vector that is reshaped from the 3 by 3 essential matrix over here. So notice that in this particular case, since we have already normalized the camera coordinates, the image coordinates with the camera intrinsic value, there's no need to do the step of normalization as we need in the algorithm to compute the fundamental matrix. The reason is because now all the camera normalized image coordinates are scaled to be within a certain scale of a unit scale from the camera matrix. And now we simply apply this to solve for the AE over here, where this is actually a 9 by 1 vector, and this A is similar to the fundamental matrix. It has to be at least a m by 9 matrix equals to 0. So we'll do the SVD, and then we'll enforce the singularity constraint over the essential matrix over here. So we will look at in the next slide how to do the enforcement of the singularity constraint for the essential matrix, which is similar but not exactly the same as the fundamental matrix. And once this is done, we can apply the decomposition on E to get the R and T, and thus forming the camera matrix. Since we know that this is the first camera matrix over here, which is I and 0 in the canonical frame, and P prime is simply equals to K and R or T over here, K prime R and T. Since we know K and K prime in the calibrated setting, after decomposing the essential matrix into R and T, we simply can recover back the second camera matrix over here. And now a look at how to enforce the singularity constraints for the essential matrix. Generally, the singularity constraint of the essential matrix is not the same as the way that we do a fundamental matrix earlier on. And but the problem arises from the same setting of the fundamental matrix, which we have seen earlier on. So we say that by computing AF equals to 0, where this is actually a 9 by 1 vector representing our fundamental matrix, is and reshaping this into our 3 by 3 fundamental matrix here. The rank of this is in general not equals to 2. It's in general equals to full rank. So the same explanation will apply for our essential matrix, where we take A, E over here, where note that this is not an epipole, I'm just abusing the symbols over here. E is actually a 9 by 1 vector that is reshaped from the 3 by 3 essential matrix over here. And in general, now by finding the essential matrix from this method over here in the linear algebra sense, the rank of the essential matrix will also not be 2. So the way to do this would be quite similar, but not exactly the same as the way that we enforce a rank constraint on F. We'll still do this E minus E prime. We want to figure out a E prime that is closest to the original matrix over here, the original E matrix over here. But it has to be subjected to a constraint that the determinant of E prime equals to 0 over here. And not just that, it also has to be subjected to the first singular value must be equal to the second singular value. So the way that to do this, it would be the same as the fundamental matrix. We'll simply take the SVD of E, and this will give us UDV transpose, where D is in general diagonal of 3 unique singular values. Since in general A is corrupted by noise, the rank of E after computing this guy over here is going to be equals to 3. So we'll simply assign the third value over here, C, to be equals to 0, the least singular value over here to be equals to 0. And we'll simply take a simple approach by taking the average of the first and second singular value. So it will be A plus B divided by 2. We'll simply set this to be the final first singular value and second singular value in the essential matrix. And we'll call this D hat over here. By plugging this back into the singular decomposition of the essential matrix of E over here, we can recover E hat, which is the closest essential matrix to what we have estimated earlier on, but it will also fulfill the rank constraint 0, which is the determinant equals to 0 by setting the last element here, as well as the first two singular values to be the same.